Okay, so this is problem number 5 from the rings and fields section of the January 2019 qualifying exam. And the problem says let R be a finite commutative ring with at least one non-zero divisor. And then part A is to show that R is a ring with unity. So we're not assuming that our rings by definition have unity for this problem. And then part B is to show that every non-zero divisor of R is a unit. Okay, so um, let's start with part A. So since we're given that the ring R contains at least one non-zero divisor, let's give it a name. So um, we'll say um, part A. Let A in R be a non-zero divisor. Since we were given one. So that means that there is no, by the definition of a zero divisor, I mean there's no um, non-zero element such that A times it will give you 0. All right, good. And now let's consider this map of sets. So this is just a map of sets. In particular, we're not claiming that it's a ring homomorphism or anything. It'll be a map phi from R to R defined by phi of x equals a times x. So it's just multiplication by a, our fixed uh, non-zero divisor a. So first of all, we claim that this map is injective. So let's show that. Suppose x and y are elements of R, and phi of x is equal to phi of y. Well, what does that mean? That means that ax is equal to ay by the definition of the map phi. So ax minus ay equals 0. And, we have the distributive laws in a ring. So in particular, we can factor out an a. So we actually have a times x minus y equals 0. And uh, remember now that a is, by assumption, not a zero divisor, since a is not a zero divisor. And note that 0 itself would be considered a zero divisor. Um, it satisfies the definition of being a zero divisor. Um, so since A is not a zero divisor, um, that means that x minus y must be 0. So x is equal to y. So what does that mean? We started with phi of x equals phi of y, and we showed x equals y. So phi is injective. And now, since phi is an injective map from a finite set to itself, we know that phi is also surjective. And remember, phi is just the multiplication by a map. So what does it mean to be surjective? Well, so there exists some b in the ring such that phi of b equals a. So phi being surjective means every element of the ring can be realized as a times something. And in particular, a can be realized as a times something, right? So that is ab equals a. So a is equal to a times something, namely this b, for some b in R. Great. So now we have we want to show that R is a ring with unity, and well, what does it mean to be a ring with unity? It means that you have a multiplicative identity. So now we want to show that R has an element that acts as a multiplicative identity, and now we have a candidate, namely this element B. So now we claim B is a multiplicative identity of our ring R. Okay, now to see this, we have to take an arbitrary element. So to see this, let R in R be arbitrary. And we have to show that B times R gives you back R. So, but we're gonna have to do that a little bit indirectly because we don't know what uh, B times R is exactly. So we're gonna do that via the map phi, which we know to be injective. So now note that phi of BR, well, phi is the map that does A times U. So applying phi to BR gives you A times BR. Now, multiplication in a ring is always associative. So that's A, B, R. And remember, B was an element such that AB equals A, right? So if AB is equal to A, then this is actually just A times R. Okay, good. And now also let's compute phi of R. Well, this is easier. Phi is just multiplication by A, so phi of R is just AR. Oh, great. Okay, so what do we know? So phi of BR is AR and phi of R is also AR. So phi of BR is equal to phi of R. But phi is injective. We just showed that. So BR is equal to R. And now since R is commutative by assumption, this suffices to show B is a multiplicative identity. So R is a ring with unity. Great. So that completes the proof of part A. And now let's go to part B. So moving on to part B, which we should recall the problem said show that every non part B said show every non-zero divisor of R is a unit. Okay, so if we want to show that every non-zero divisor of R is a unit, then we should start by letting A be a non-zero divisor. So let A in R be a non-zero divisor. Uh, this terminology with the dashes can be a little bit confusing because sometimes we talk about non-zero zero divisors and but here we just mean an element that is not a zero divisor. Don't get confused by that. Um, I probably would prefer to say let A be an element that is not a zero divisor. Um, okay. Um, then since R is a finite commutative ring, we can talk about its cardinality. So let's let n, let's call the cardinality of R, let's call that to be n. Okay. And now we need to make an observation. So observe that since A is not a zero divisor, no power of A can be a zero divisor either. Okay, so let's prove this claim by induction. So just to be totally sure of it, if some power of A were a zero divisor, then there would be a least power of A that is a zero divisor. So we're proving this subclaim by contradiction. Right, so supposing that some power of A is a zero divisor, well then by the least number principle, which is equivalent to the principle of mathematical induction, there would have to be some least power of A that is a zero divisor. And let's call it M. So A to the M is the least power of A that is a zero divisor. So then A to the M times some B is equal to 0 for some B that's not 0. And then let's rewrite this as A times A to the M minus 1 times B. That also has to be 0. But since a to the m minus 1 is not a zero divisor, since a to the m was the least power of a that is a zero divisor, a to the m minus 1 cannot be a zero divisor. And since b is not zero itself, a to the m minus 1 times b cannot be zero. So the fact that a times a to the m minus 1 times b is equal to 0 means that a is a zero divisor. So a is a zero divisor, which is a contradiction. Okay, so this proves the observation that no power of a can be a zero divisor. And recall that since 0 is a zero divisor, this also means that no power of a can be 0. Okay, good. So that was our little subclaim. Now let's remember that n is the cardinality of R since R is finite. And let's uh, move on. So let's consider this list. Consider the list a to the 1, a squared, a cubed, dot, 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 a to the n, or n is the cardinality of R. This list cannot include 0 since no power of a is a zero divisor. And in particular, no power of a is 0. Okay, so this list of n items cannot include 0. N items, all of which are elements of the ring, and it can't include 0, but 0 is an element of the ring. So that means that by the pigeonhole principle, as the cardinality of R is equal to n, there must be two elements or two items, let's say items on this list that are equal to each other. Right? They can't all be distinct because they're n many of them and they don't include 0, which is one of the elements of the ring. And n is the cardinality of R. So there have to be two that are equal to each other. In other words, a to the I is equal to a to the j for some I and j between 1 and n with I less than j. So thus a to the j minus a to the I is equal to 0. So now we can use the fact that we have a unit, we have a unity, we have a one, we have a multiplicative identity. We showed that in part A. We can use the fact that this is a ring with unity to rewrite this using the distributive law as a to the I times a to the j minus I minus 1. We have a 1 in this ring. We know that now, which is equal to 0. Okay. So let's move to the next page. So I'll rewrite that line. Okay. Again, we have a to the I, a to the j minus I minus 1 equals 0. This is what we have. And now, since a to the I is not a zero divisor, remember we proved as a lemma that no power of a was a zero divisor. So since a to the I is not a zero divisor, that means that a to the j minus I minus 1 is equal to 0. So a to the j minus I is equal to 1. So we can rewrite that as a times a to the j minus I minus 1 is equal to 1. And, well, what does that mean? That means a is a unit, because we found something that we can multiply it by to get 1. And that completes the proof of part B. We wanted to show that every non-zero divisor of R is a unit. And we did need that the ring was finite for part B. We didn't need that there actually was at least one non-zero divisor directly in part B, but we needed it for part A, and then we used part A in part B when we showed that there was, when we used the fact that there was a 1 in our ring for part B, so we needed all of the hypotheses. And that completes the proof of the problem. Thank you.